How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at equilibrium, and our objectives are going to be to explain what an equilibrium is and what conditions must be met in order for it to exist. So kind of a simple video. One concept. So equilibrium. Basically, there's a forward and a reverse process that are occurring at equal rates. So my go-to analogy, it's like running on a treadmill. Because even though overall there's no change over time, you're not going anywhere on that treadmill, both processes are still occurring. You're running forward on the treadmill, but it's moving you back, hopefully, at the same speed at which you're running forward. So the rates are equal. How fast you're running forward is how fast it's moving you back. So hopefully, you stay on that treadmill. If that's not true, you get thrown off, right? So in equilibrium, it's the rates that are equal, all right? The rates are equal. So the amount of products and reactants do not need to equal each other. You don't have to have equal products and reactants. They just have to remain unchanging over time. They don't have to be equal to each other. Because the forward and the reverse reaction rates are equal, it's telling us we're making products at the same speed we're recreating the reactants. So overall, the amounts of them don't change. Right? So first, let's say in this example, we started with a lot of reactants and we started with no products. As the reaction proceeds, well, I'm using up reactants, so they decrease, and I'm creating products, and they increase. And then the reverse reaction rate is going to get to the point that it's equal to the forward. So right about here, I think, equilibrium is achieved. Because the amount of reactants and products remains constant over time as both forward and reverse reactions occur at equal rates. As quickly as I'm making products, I'm recreating the reactants, and they stay at a constant level over time. All right, so we got physical equilibrium where we're talking about physical changes. So an example could be like phase changes, where we have, let's say this is my water bottle. Where's my pen? And let's say it's partially filled with water, right? All this is water. And it's sealed at the top, and I left it out somewhere over time. And I came back to it, and I was like, oh, hey, look, there's water droplets all over the upper part where the water shouldn't get. It was sitting there stationary. It's not like it got shook and all of a sudden I have drops forming on the top of there. How'd they get there? Well, some of the water evaporated. It went from the liquid phase into the gas phase, and then it condensed onto the surface of the water bottle. So over time, that whole process is going to reach equilibrium. So as quickly as it's evaporating, it's going to be condensing onto the sides of the bottle or back into the rest of the water, and then an equilibrium is going to be achieved. So we're talking about like H2O. In a liquid phase, it's going to evaporate and become H2O gas, and then eventually the reverse reaction rate is going to be equal to the forward, and we're going to get in equilibrium. So at equilibrium, water is still evaporating, but it's also condensing, and the rate at which that's happening is equal. So chemical equilibrium can exist when a chemical process is reversible. So there's a forward and a reverse reaction. Right? So not all chemical reactions are reversible or will reach an equilibrium. So this isn't true for all reactions. Some reactions can reach an equilibrium, but not all of them. So equilibrium is represented by a double arrow, illustrating that there's a forward and a reverse reaction. So if you see something like this, where you have a double arrow, or maybe sometimes it's like a single line with half an arrowhead that way and half an arrowhead that way, that's showing that it's at equilibrium. Or sometimes it's like this. It's saying that there's a forward and a reverse process, and they're at equal rates. So I'm going to try to visualize this for you guys. So we got reactants making products, and we got this double arrow here showing us that it's at equilibrium. So even though the amounts of reactants and products doesn't change over time, the forward and the reverse process still occurs. So let's say this system is at equilibrium. We're going from red to, that's kind of like a purple, and we're at a equilibrium. Well, reactants are making products still, and products are making reactants still. So it's something kind of like this going on. So the changes are still happening, but the rates are equal to each other. So at any given time, we have the same amount of products over time and the same amount of reactants over time, but the equilibrium is forward and reverse reaction. So when can equilibrium exist? We already talked about how not every reaction can find equilibrium or, exist as an equilibrium. So the ones that can, you still need to meet some conditions. So it needs to be a closed system. If either the reactants or the products can escape the system, then it's only going to proceed in one direction. It can't have a reverse reaction if all my products are leaving, right? So it needs to be a closed system. So an example would be like a soda bottle that has the following equilibrium. You got CO2 gas making an equilibrium with it being dissolved. So when you close that bottle, it reaches equilibrium. As soon as you open it up, you hear that psst, and some of the gas can escape. You can no longer have an equilibrium. All of that dissolved CO2 is going to escape as a gas once you open it up. The other condition is that the opposing rates have to be equal. So as quickly as you're making product, you have to be making your reactant. And those are the two things. Right? So summarize. Explain what an equilibrium is and what conditions must be met in order for it to exist. That's it. Okay, bye.